today we have visiting us Cora Uhlemann from the University of Munich, where she is a PhD student. This is her first visit to North America, so we're very happy to welcome her here. And she's going to talk to us about the large-scale structure of Schrodinger.
Yeah, thanks. Thanks for having me here. Today I will talk about cosmological structure formation and a special method which is able to describe it analytically. So first, what are we talking about? So first I will talk what is structure formation, why is it interesting and relevant to cosmology. Then how can we actually analytically describe the evolution of cold dark matter, which is a main ingredient of our standard model of cosmology. I will first present the standard model, which is the dust model, and then I will present the method we kind of advocate for, which is the Schrodinger method. In the end, I will present some work going on as a first application of this to compute correlation functions of both dark matter and dark matter halos. So the basic question of structure formation is, how did the universe evolve from a hot, dense, but nearly uniform initial state into a state which basically features structures on nearly all scales? So from stars, planets, galaxies, clusters, which are all aligned along the cosmic web. And cosmology is providing an answer to that question. First, the first era of inflation tells us how primordial quantum fluctuations get converted to the initial conditions for structure formation. And then structure formation sets in and tells us how a quite homogeneous distribution with only tiny, tiny perturbations gets actually converted into the whole structures we can see in the cosmic web today. So what happens during inflation? So the first stage of inflation is a stage of quite accelerated expansion. During this stage, tiny, tiny quantum fluctuations get eventually amplified to provide the initial conditions of our universe. So homogeneity, isotropy, and flatness. So this was dubbed the most boring initial conditions we could think of. Inflation, due to this quite rapid expansion, also helps to cool the initially hot plasma down, which finally allows the atoms to capture their electrons and recombine. After recombination, photons decouple and can now travel freely, which is exactly the reason why we can see the cosmic microwave background, which originated 380,000 years after the Big Bang just today. The cosmic microwave background has been mapped by several satellite missions, beginning with COBE, over WMAP, and lately Planck. And it basically established that it's a quite homogeneous distribution with only nearly Gaussian deviations of about 10 to the minus 5 in density contrast. And exactly those tiny fluctuations serve as seeds for structures to congregate around. So structure formation happens hierarchical. That means the smaller structures form first, and then they merge into each other, forming the greater structures. Dark matter plays an important role there because dark matter does not experience any counteracting forces for gravity, such as radiation pressure, which is relevant for baryons and, for example, leads to this baryon acoustic oscillations. So dark matter are the first structures to be formed and quite important to support the gravitational potential where galaxies and clusters form in. So the tiny overdensities starting out with 10 to the minus 5 act as seeds and gravitationally attract matter to form eventually bound structures. And we can understand this process quite easily from a conceptual point of view, but describing it analytically is quite hard. So in the linear regime, when the density contrast is still below 1, it is analytically understood, and we can describe cold dark matter basically as a pressureless fluid. But as soon as we enter the nonlinear state, which is quite important for structure formation, this is so far analytically not accessible, and we have to resort to n-body simulations which tackle this problem numerically. I prepared a small sample here. As you can see, initial Gaussian deviations get converted into this nice structure of the cosmic web with sheets, filaments, and the structures in between. So what do we want to describe? We want to have a theoretical double for this n-body simulation. So we want to have a tool which actually allows us to understand the basic properties analytically. And why is this important? So the cosmological standard model tells us there's only 5%, which is basically all we can see in galaxies and clusters, are the baryons provided and described by the standard model of particle physics. So basically, most of our universe is of unknown dark origin. First, we have dark matter, dark energy, which basically tells us what is the expansion history. And it is quite good accuracy, can be assumed to be a cosmological constant. On the other hand, we have cold dark matter, which is especially important for large-scale structure formation. And cold dark matter can be assumed to be collisionless, meaning that it interacts only gravitationally, and it is initially cold, meaning that it can be described using a smooth gradient field in the first stages. And cold dark matter leads to the large-scale structure of the universe, where dark matter halos are basically surrounding most of the galaxies and their clusters, which is actually the reason why it is important for galaxy surveys. Since by mapping the galaxy in galaxy surveys, we can actually constrain cosmological parameters. So describing what is going on there is quite important to improve our model over the parameters. On the other hand, dark matter halos are quite special objects. For example, numerical simulations reveal that they have striking universal features, such as halo density profiles. And we want to understand the origin of this universality from a theoretical point of view. So now that you are hopefully motivated, that is important, how can we describe cold dark matter? And especially, how can we use the Schrodinger method to do that? So cold dark matter can be conveniently described using a distribution function. The distribution function basically encodes all phase space information. And we can easily say what is expected to happen during structure formation. So we start out with cold initial conditions. That means we have basically particles sitting in some region of space with negligible velocities. And what will happen now due to gravitational instability, the particles will start falling inwards. So the particles in the outer regions will accelerate and move towards the center. So you can see in phase space, this looks like that. We are starting with a really flat phase space sheet. And since the particles on both sides will receive a velocity, the phase space sheet will begin to bend, because the particles on the left-hand side will get a positive velocity and the particles on the right-hand side will get a negative velocity. So what will happen during the first stage, there will be a coherent infall and this phase space sheet will just bend a little bit. But what will eventually happen, those two streams falling inwards will cross each other. And when they cross, the phase space sheet basically wraps up. And as you can see there, at this point you have multiple streams. That means if you're sitting at one position in space, there are several particles, one going through in this direction and one going through in that direction, and maybe another particle sitting at rest here. So there will be a coherent infall, then a turnaround, and this is exactly the point where these multiple streams become important. And we want to model this from a theoretical point of view. And what we already know that in n-body simulation, this happens just as I described it to you. So in an n-body simulations, you don't really have a phase space sheet, but you see the individual particles sitting there, which is why here's some scatter. But what will happen, you will see these multiple streams form, and this sheet will wrap up. And eventually, this will lead to the formation of a bound structure, so a dark matter halo. And what is now quite interesting, there has been proposed a method called the Schrodinger method by Vidra and Kaiser around 1993. And they employed the Schrodinger equation, solved the Schrodinger equation, and showed that you can build a distribution function out of it, which actually resembles the n-body simulation. So you can see, using the Schrodinger method, it really seems as if you are able to describe what is going on during structure formation. And we got inspired by this method, and we now want to employ it analytically. So from an analytical point of view, what is our task? So as I said, we start off with n identical particles, and we can easily build a distribution function out of them, just by multiplying delta functions in position and momentum. And from this, we don't get a proper phase-space distribution function which is continuous. So we have to perform an ensemble average. And if we perform this ensemble average, we can assume that no collisions are taking place. The nice part about gravity is actually that collisional terms are suppressed by 1 over n when n is the number of particles. So if we have lots of particles, we are actually safe at neglecting those collisional terms. And if we do that, we see that dark matter can be perfectly described by the coupled Vlasov and Poisson equation. So the Vlasov equation just encodes phase-space conservation, and the Poisson equation encodes gravitational interaction. But as you can see here, of course, the gravitational potential will depend on the distribution function. So now you can say, okay, we have our describing equations, perfectly fine. So the only task we have is just to solve it. Unfortunately, this coupled equation is quite complicated because first, it is nonlinear, since the potential depends on the distribution function itself. It's a partial and even an integral differential equation, since the gravitational potential depends on the number density. So basically, the integral over momentum space of the distribution function. And the next bad part, it has 7 variables. So we have momenta, positions, and time. So as you can imagine, solving this is quite hard. So we now have to think of how can we reduce the information content there in order to be able to solve it. And a straightforward idea to reduce the information content is to say, okay, let's say we are not really interested in the whole phase space information, but just in the spatial information. So spatial information will tell us what is the density at any point in space, what is the velocity, and so on. If you say, okay, let's restrict to that, you actually are interested in so-called moments of the distribution function. So you multiply with momentum several times and integrate over it. So the 0th moment will just give you the density. The first moment will tell you what is the velocity. And in the higher moments, you will see something like velocity dispersion and so on. And as you can see there, the second moment has a trivial part, which is just related to velocity, and an extra part, which is the cumulant. And now you can ask, okay, which is the evolution equation of density, velocity, and velocity dispersion? You can actually derive it from the Vlasov equation, and it's quite simple. But unfortunately, it's an infinite coupled hierarchy. That means if we want to determine the time evolution of density and velocity, we have to specify what are the higher cumulants. So we have to say what is velocity dispersion. So that now tells us, okay, we have to somehow close this hierarchy. And the easiest thing one can imagine is maybe we can just truncate it. Truncating means we say, okay, maybe just higher cumulants are not that relevant. So as a first step, we can imagine, let's just take density and velocity and neglect velocity dispersion and all higher cumulants. And this is exactly the only consistent truncation you can do. So if you just stick to density and velocity, you arrive at the dust model. The dust model is basically describing cold dark matter as a pressureless fluid. And you have the number density at every point and a well-defined momentum at any point. So you can describe the velocity just using a velocity potential, so you have no curl or whatsoever. That means now instead of solving the complicated Vlasov equation, we can just solve the fluid equations which determine what is density and velocity. And this seems quite nice. And indeed, it's a good description for the first stages of the evolution. So when the phase space sheet slowly begins to bend. But in the end, you can immediately see that this model will have to fail. Because in the end, we want to describe multiple streams. That means at any point, at one point in space, we have several velocities. And this cannot be described using the dust model because at any point there's only one well-defined velocity determined by this potential. So the dust model is really limited to the single stream region, and we cannot describe halo formation with the dust model. So now we have to think, how can we improve the dust model? And an important part is that the dust model is restricted in the sense that it has only 2 degrees of freedom, just density and velocity. And we want to keep this simplicity. So we just want to have a low number of degrees of freedom and describe the whole distribution function by this means. So what we see, if we want to have a theoretical n-body double, we want to solve the Vlasov equation, which is kind of quite hard. So we thought about good models, and the first model is the dust model. It works quite well in the first stages, but will fail when shell crossing happens. So what is an interesting observation is, if you take the so-called Wigner distribution function, just from quantum mechanics, which is connected to the Schrodinger equation, and you build a distribution function out of it, and you actually see that the equation just looks like the Vlasov equation plus some corrections. And at this point, you might think, oh, nice. If I'm solving this problem, it seems as if I'm actually solving the Vlasov equation with some tiny corrections. The problem is that although the equations look similar, their time evolution is not. So you cannot use this. But there's an easy cure for that. You can just say, OK, let me not stick to quantum mechanics, but just stick to a coarse-grained description. So basically, we have a semi-classical model. And what happens then, you actually don't want to solve the Vlasov equation anymore, but a coarse-grained version. A coarse-grained version basically just means you're taking small smoothing scale and remove the information which are below the scales. And you can actually see, OK, that's actually a good point of view if I want to compare with an n-body simulation, because in an n-body simulation, you also have a finite resolution, which is then kind of your numerical artifact. So and the nice part is this actually gives us a connection between the Schrodinger equation. We can build a distribution function out of it, and it solves something like the Vlasov equation. And their time evolution is in good correspondence. So now you can ask, OK, what should the Schrodinger equation have to do with the Vlasov equation? And how can I actually do this? So
is that effective because you're smoothing and eliminate multiple screens below some scale?
Yeah.
You haven't really explained the Wigner.
Basically, you can think of it like that. With this h bar, you introduce something like a quantum scale. And in the end, you have to ensure that you don't resolve this quantum scale. So that is the reason why you have to employ this coarse graining. I will comment on this after the slide. OK? So what you're basically doing now, you say, OK, I can describe cold dark matter by means of a self-gravitating scalar field. And a self-gravitating scalar field has only 2 degrees of freedom, just the amplitude and the phase. And this so-called wave function just have to solve the Schrodinger-Poisson equation. So it looks like the ordinary Schrodinger equation, but it's nonlinear, because this potential is determined by the Poisson equation, just in the same sense it was for the Vlasov equation. And the interesting part is now, quantum mechanics tells us how we can map a wave function to a distribution function. And this is just called the Wigner function. So don't be scared. So the last part is the Wigner function. It just tells you, take your wave function, add a special momentum dependence, and you get a distribution function. Then there is a small technical problem. Namely, the Wigner function is not a probability distribution. So it can go negative in some small regions. And this is exactly the reason why you have to employ this coarse graining. So this coarse graining basically just smooths a little bit out the small scales and ensures in the end that you are not able to dissolve this quantum h-bar scale. So 2 parts. The one part is the Wigner function, which is quite nice because it tells you can describe your distribution function, which is a function of momentum and space, now just using a wave function, which is just a function on space and has just the 2 degrees of freedom amplitude and phase. So this is a somehow reduced information content, and only 2 degrees of freedom are quite nice.
So the parameters in the x and sigma, what exactly here?
Exactly. I will now comment on the parameters. So the first part is the sigma x and sigma p are the coarse graining scale and basically tells you what is the fundamental resolution. So you have to ensure that sigma x and sigma p are bigger than h bar. And if you compare this to quantum mechanics, you can see that it's something like the uncertainty principle. So in quantum mechanics, this will be the uncertainty principle, but here we don't have quantum mechanics. And actually, this h bar is not a quantum mechanics value of h bar. It's just a computational value. And h bar has a quite interesting role. So on the one hand, it tells you to which accuracy you are solving the Vlasov equation, because you are actually not solving Vlasov plus, but Vlasov plus corrections. On the other hand, this h bar also controls how special is your ansatz here. And actually, it's interesting because some people argued you have to send h bar to 0 because in the end, you really want to solve the Vlasov equation. But you cannot do this because if you send h bar to 0, you can reduce this whole complicated model and you get back the dust model. So h bar has a quite interesting twofold role. On the one hand, you want to keep it small since you are then solving the Vlasov equation quite accurately. On the other hand, you cannot send it to 0 because then your model is the most restricted one.
So is there a maximal phase space density the way that you've written down the distribution function? I can't tell from this.
You mean if there is a maximum value for f, or?
Yeah, I guess, right? Because your coarse graining, right? So the actual phase space sheet for CDM will have infinite density, but you coarse grained it on some scale in phase space.
Yeah.
So it corresponds to a maximal phase space density.
So you will later see that our phase space sheet is actually not really thin, but has some extent.
Right, so you're coarse graining on the sigma x.
Yeah.
Yeah, so does that correspond to a maximal density on this?
So if you mean that you avoid singularities by that, then yes. So for the dust model, you will run into density singularities, and this will be regularized if you use this prescription. So in this sense, yeah, but that is not really connected to the coarse graining, but more to the h bar. I will show the evolution then. Next slide. Okay? Okay.
Another way, what you've done is to take effectively the velocity potential at the end and combine them into psi, which is a fine thing to do. But if you leave it in the original variables, which is the Bohmian approach to quantum mechanics, then one of the ways that one describes what quantum mechanics does is the addition is to identify either a quantum potential or a quantum.
Exactly.
But it depends upon the density gradient, the information content. And what it does is that it tries not to overly concentrate things. That's the nature of it. It is in an information sense. It says that the information can be too concentrated. So, and an issue which I'm sure you will address is that effective pressure or potential that you're adding has really, right, you've got nothing to do with the system that you are, it's just a phenomenology. And the question is, can it be used for anything more than that? Because it's not actually describing, I think, unless you show it differently, it's not actually describing what the full-up dynamics is, which we can simulate with high accuracy.
Exactly. So that was just the next point. So what you can actually see, and in a way you can understand by this, if you send h bar to 0, you just arrive at the dust model. So you can take the Schrodinger equation, take the wave function in this amplitude and phase form, and from this you can derive equations for amplitude and phase. And if you do that, you just see, oh, I'm recovering something like the fluid equations, but here's this extra term. And this extra term is exactly what Dick was talking about. It constitutes some kind of a quantum potential, quantum pressure, quantum velocity dispersion, however you want to call it. So it's an extra term here, and it indeed depends on the gradient of the density. And here you can see, okay, if I'm sending h bar to 0, I just recover the old dust model. And this H bar is quite important because on the one hand, it will avoid that singularities develop, which are present in the dust model. And on the other hand, this H bar kind of helps to emulate this multi-streaming. So you can imagine it like that. Actually, this H bar is like a pressure. That means if you have a collapsing structure, the pressure will push outwards. And this will actually not describe what is real multi-streaming, but if you coarse grain over it, you cannot distinguish between a bouncing off and a going through. And this is exactly the kind of secret behind this H bar. Combined H bar and the smoothing scales, you can emulate the multi-streaming. And I will show you in the next slide just a small example. So we wanted to be sure that this method actually works. So we did a 1D example, just pancake collapse. And we evolved the Schrodinger-Poisson equation in time. And then from the wave function, we built a distribution function according to the formulas shown there. And now you can compare what is the phase space density and how does the evolution look like. In the following, you will see a blue curve, which is the Schrodinger method, and a red curve, which is basically the dust model. So you can somehow cure the singularity in the dust model and just develop it through the first time of shell crossing, but you will see it deviates from this point. So we start with this phase space sheet, which has some extent. It slowly begins to bend, and at this point, the dust model is in between here. Now shell crossing happens, so now multiple streams will be important. And as you can see here, the Schrodinger method indeed describes this multiple streaming region, but the dust model will start to fail here. So it basically will just propagate it through, and there won't be a turnaround for the dust model. So you can see here, if you solve the Schrodinger equation, you do not run in any singularities. And if you construct a phase space distribution function, you really see a similar behavior as is shown in an n-body simulation. And now the first question you could ask is, okay, that's nice. If we actually can describe multi-streaming, do we see in the end something like a virialized structure? So can we describe halo formation by that? And indeed, it is possible. I just showed the same video, a little bit speeded up and evolved further. So first moment of shell crossing, multiple streams here. The dust model fails. But now you can see here, second time of shell crossing, and slowly but surely it will evolve towards a bound structure. So
like dust model, like you use means although, is that what you mean?
yeah.
That's just first order perturbation theory.
But in 1D, it's the exact solution.
Well, but you aren't comparing with the Sommerfeld, what we call the Sommerfeld approximation, because that is exactly what it is.
Yeah.
And you're saying that there are deviations.
It is an exact solution, but it's not describing the actual dynamics. So that is, you can imagine the dust model is identically solving the Vlasov equation. But since it is a restricted model, there's no guarantee that it will really describe what is going on there. And exactly the reason is there will be a singularity during shell crossing, so there's no guarantee afterwards that you're capturing the right solution. So that's an interesting property because it is actually the analytical solution in 1D. Yeah.
Yeah, I think I'm kind of baffled. Wait, okay, so like, so you're solving here a 1D system.
Yeah. So we are solving the Schrodinger equation and construct a distribution function out of it.
And so your statement is that is that for this problem you're solving, Zotovich is the exact.
No, it's not for the wave function we are solving for.
No. So for the actual, like, the actual n-body case, let's say, Zotovich would be the exact solution. Right?
It is an exact solution to the Vlasov equation, but not the one that would correspond to an n-body simulation. Because it's actually, you can see the dust model will have a singularity in density when you have the shell crossing point. So afterwards, so you can somehow propagate it through and it stays a solution, but it's not the right one. You can think of it, if you run through a singularity, you really have to take care not to follow a solution basically on the wrong way. And although it is an exact solution, it is not the one describing n-body dynamics.
I thought the dust model you said was single value at a given time.
Yeah.
But that's not single value.
Yeah, because that's basically a way to heal the dust model and propagate it through the singularity. And that's actually the reason why you can see until shell crossing, it's perfectly fine. But afterwards, what will happen, the streams will just go through each other. And this just tells you that's not a proper description, because if you have gravity, the streams will cross and then come back, of course.
Depending on the potential.
Yeah, of course. But if there's matter in the middle and they will cross, they will come back.
It's just that the shells that are crossing, the mass enclosed can change, but the streams do. I mean, that's the whole phenomena of galaxy, these splashes that people see, right? I mean, it's the same phenomenon.
So what you actually can do, for example, in simulations, you can make it, so after it will just go through here, you can make it stick, and then it will actually describe the large-scale properties. So the sheets and filaments, you can describe them.
Before you go on, so is there free parameters here at sigma x and sigma p?
So basically what we did here, we chose an h bar, which is like 10 to the minus 5, which shows this nice behavior. And then you can just determine what are the proper smoothing scales to ensure that your phase space distribution is positive.
Can you make H bar canonical variable?
In the end, you would think of, so I will comment in the end about the role of h bar. So actually that would be really interesting to make it a kind of variable, because what you see, if you're choosing h bar bigger, it will take longer to form the structures. And in this sense, you might think of, okay, maybe I want to have like a flow in h bar, because it could be some kind of a phase transition. Do I form halos or not? Yeah, that would be interesting for sure. So we saw that the Schrodinger method is basically on this numerical example, and there have been other studies capable of describing these multiple streams. But now you can ask, so why can I describe, just using the 2 degrees of freedom, all high accumulants just at velocity, dispersion, and so on, which are important to describe these multiple streams? So let's see how this is possible. Let's get back to this distribution function. There's a specific property which is quite nice. So the special momentum dependence of the Wigner function here will actually allow us to compute all the cumulants analytically, because we can really perform the integrals. And what we see then is the first cumulants are just as usual, something like density and a velocity. In this sense, they are connected to the amplitude of and the phase of the wave function. But now the coarse graining also comes in. So what you are actually observing is not a real microscopic density, but a macroscopic one, which is smoothed on some scale. And for the velocity, this is a similar thing. And what you actually will have is a mass-weighted velocity. So you have to smooth the product of density and microscopic velocity, and then divide by the coarse-grained density. And this will have an interesting effect I will show later. And what is indeed possible, I can give formulas for all the cumulants, so second cumulant, velocity, dispersion, and so on, which are just described in terms of this 2 degrees of freedom. So in some sense, you restricted your model because you have only this 2 spatial degrees of freedom, but still they are all cumulants present. The thing is that they are, of course, restricted and connected to density and velocity. So it is a special form of the cumulants, but they are all there. And that's especially important if you actually want to close the hierarchy I talked before about. So you can think, maybe we could just take the dust model, and we know that velocity dispersion becomes relevant when I have these multiple streams. So you could think of, okay, maybe let's add some velocity dispersion just by hand, because velocity dispersion is what is missing, add it there, and maybe the model will be better then. The problem is that after shell crossing, so after this point when multiple streams become relevant, not only velocity dispersion, so the second cumulant will be relevant, but also all higher ones. That means you have to have a model which after shell crossings give you all cumulants and source them dynamically. And that is actually what the Schrodinger method does. So I plotted here the first three cumulants. So the first one is just the velocity. And as you can see, velocity is always important. So this is time evolution. At a equals 1, shell crossing will happen. And as you can see here, velocity is always important. But velocity dispersion, which is this curve, and a third cumulant will just kick in after shell crossing and be as important as velocity and of an equal value, basically. So this tells you if you really want to describe multiple streams, you have to somehow turn on all cumulants just after shell crossing. So you have to source them dynamically. So there's no point of just taking a model and adding one cumulant, because this won't show this behavior. So in some sense, this is the secret of the Schrodinger method and the reason why it's able to describe this multiple streaming.
So for this 1D system, you can solve it numerically.
Yeah.
And you could plot those.
Yeah, exactly. So this is just one slice. I think it's 0.5 megaparsecs, so something around here or something like that. Because you can, so you have to plot the cumulants at any point, and we just took one slice to illustrate it, the time evolution.
You're not comparing to the exact solution?
No, here not.
Okay.
So we are just comparing what are the properties of the Schrodinger method, how do the cumulants typically look like, exactly. So now that we discovered that the Schrodinger method works, one could ask, okay, what can we do with it? So we now know we can solve a Schrodinger-Poisson equation instead of the Vlasov equation, and it really looks similar to an n-body simulation, and in the end we get something like a bound structure. So this would be interesting to investigate. However, as a first step, what we did was to investigate the coarse graining, because the coarse graining is quite important here. They thought, okay, let's first concentrate what are the consequences of smoothing your distribution function. So this is kind of the first application. So I will now tell you how we can determine the dark matter power spectrum, so something like the correlation function, with what is called the coarse-grained dust model. So we will say, we know that the dust model fails after shell crossing, but in the first stages, it's a perfectly fine model. So it works quite well in the early stages. And there you can solve it perturbatively. And now we will stick to the coarse-grained dust model. On the one hand, you can think of it, I take a dust solution and coarse grain it. But on the other hand, it is also a limiting case of the Schrodinger method. Because if I send h bar to 0 here, I will recover the coarse-grained dust model. And what is quite interesting, so for the dust model, you can just do ordinary perturbation theory. I take my fluid equations. I now say, okay, I'm not interested in the number density, but in the density contrast, so the deviation from 1. And I will encode my velocity basically in a scalar. Because there's no vorticity present, I can do that. So now I have two variables, and I can just expand them perturbatively. And you can just do a separation ansatz if you concentrate on the fastest growing mode and solve the equations perturbatively. And from that, if you switch to Fourier space, you can derive the power spectrum. And the power spectrum will give you the correlation function. So the correlation function tells you basically what is the excess probability of finding two objects separated by some distance. And if you have nice symmetries like homogeneity and isotropy, it's just a scalar function of the radius. So if I imagine I have a random Poisson distribution of particles, my correlation function will just be 0. If I now imagine I have a distribution where there's some radius where there are more particles and some radius where there are less, then I will see a correlation function with a peak and a defect at another point. And to describe the correlation function, if we go to Fourier space, we just have the power spectrum. And the correlation function I will later also talk about is, for example, you can say, what is the galaxy correlation function? If I have a galaxy at a certain point, what is the probability of finding another in a certain distance? And this is a powerful probe for cosmology, and you all know about, we can read off baryon acoustic oscillations, which are basically a standard ruler. But I will talk about this a little bit later. So if you just concentrate on dark matter, you can derive the power spectrum, for example, for density. And as you expect, if you just do linear perturbation theory, the power will go down on large k, which is just small scales. And if you consider now one loop corrections, the power will go a little bit up. And now you can ask, what is the effect of a coarse graining there? As you expect, the coarse graining will just remove power on small scales. So you expect the density power spectrum to be bent down. And that's actually what happens. So if you coarse grain on some scale, you will remove the power on those scales, and the density power spectrum will just go down. So that's kind of boring. But what is quite interesting, I talked before about the velocity. The velocity, which is connected to a coarse graining, will be a mass-weighted one. And this has an interesting consequence. So even if your microscopic velocity has no curl, so there's no vorticity, your mass-weighted velocity will pick up a term. And it's quite interesting if you derive, just using perturbation theory, the vorticity power spectrum in one loop, and you compare it, so we plotted here for several smoothing scales. As you can see, if I tune up the smoothing scale, vorticity will become relevant on larger scales, because the larger scale you are smoothing, the bigger the large scale vorticity will get. But another interesting property is that basically the shape stays the same, and you just shift it towards smaller k. And what we did, we just compared it to an n-body simulation. So you can measure vorticity in an n-body simulation. And what has been observed there, so there are several simulations with different mass resolutions. And as you can see there, if you increase the mass resolution, your curve will actually shift, but eventually it will somehow converge. And an interesting thing is if you compare this converged curve here to our expectation, the 1 megaparsec smoothing scale will do the job. So you can describe this large scale vorticity, which is observed in an n-body simulation, that it is effectively a large scale vorticity which just comes from smoothing. And that's quite interesting. And you can even compare like the shape parameters of this, and it's quite good. And another interesting point is there's some theory of effective field theory of large-scale structure, which is also connected to this and gives you a prediction of the shape of this curve. And it's also in quite good correspondence to the coarse graining. So let's leave this aside. We know we can do perturbation theory just perfectly analogously, and we get something like vorticity. But another interesting point, we can now ask, okay, usually we are not interested in the dark matter correlation function, but more in the correlation function for halos. Because the correlation function for halos will be connected to the correlation function for galaxies, which are inside halos and somehow trace them. So we can determine this halo correlation function from the coarse-grained dust model. And I do not know how many time do I have left.
Oh, you're good.
Okay, I'm good. Okay, perfect. Okay, fine. So if we want to describe the halo correlation function, it's clever not to describe it using this density and velocity picture, but rather using what is called the Lagrangian perturbation theory. So we are not describing it using density and velocity, but using the so-called displacement field. The displacement field just tells you how to displace initial particle positions q to their final positions x. So we can now perform perturbation theory in this displacement field, and it has really better properties than a Eulerian picture. And then we have to somehow relate it to the density we are observing in the end. And this is a nonlinear relation. So we can first perform this perturbation theory here, and then we have to perform this mapping. And what is quite popular is the so-called Zeldovich approximation. The Zeldovich approximation is just first-order perturbation theory in this Lagrangian space. And if I convert it back to the density, I can actually perform this directly. So I can do the relation non-perturbatively. And if I do that, I get a resummation of the standard perturbation theory I showed before. So it's a physically motivated resummation, and it really describes good what is going on there. And what has been asked, so we have this nice approximation, the Zeldovich approximation. How can we improve it? And what has been observed if you take the prediction from the Zeldovich approximation and just take your input power spectrum and smooth it on some scale, and then compare it to the simulations, you actually see if you smooth your initial power spectrum, you improve the agreement with the data. So that has been just an interesting observation. And we got inspired by this and thought, okay, smoothing a power spectrum is related to the coarse-grained dust model. So let's really investigate what are the consequences of considering a coarse-grained dust model. And another evidence which motivated us was what we did. We took an n-body simulation, marked all particles which were sitting in the final halo. And then you can trace them back to the proto-halo. And now you can ask, in which, I want to predict the displacement field using the Zeldovich approximation. And there you can say, oh, maybe I use the Zeldovich approximation combined with a smoothing. And now you can ask, which smoothing scale gives the best prediction compared to the simulation? And what is interesting, what you observed there, if you take your proto-halo and you smooth it on the Lagrangian scale, so basically the size of the halo in the end, you will get the best prediction for the displacement field. In this sense, you have to keep in mind that halos are really different to dark matter particles. So for a dark matter particle, it is somehow artificial to introduce the smoothing scale. But for a halo, which is really a composite object, it perfectly makes sense to somehow smooth on the scale of its radius.
So that's exactly what Atlas does in the Lagrangian theory for halos. You know, this is something we're continuing to work on heavily, but that's so in fact the displacement is adapted in that model and it works very well compared, relatively well, I should say.
Yeah. And this observation motivated us to ask, okay, what does the theoretical implementation via this coarse-grained dust model would tell? So we combined the coarse-grained dust model with this Lagrangian picture. And in the end, we want to improve the Zeldovich approximation by saying, okay, let's not do first-order perturbation theory, but also higher order. And if you do that, you get something like the post-Zeldovich approximation, so higher order perturbation theory, and then you have to still convert it to the density. And in this sense, it is not possible to do it non-perturbatively as for the Zeldovich case, but you can leave it partially resumped. And this is then called convolution Lagrangian perturbation theory. But that's just a technical aspect. So basically the idea is combine the coarse-grained dust model with Lagrangian perturbation theory, and in the end we want to predict the halo correlation function. The motivation why you want to predict a correlation function, you want to compare to actual galaxy surveys. But if you want to compare to observations, observations are made in redshift space, not in real space. And there, of course, the velocities will affect what you're actually seeing. Because if you neglect gravitational lensing, the parallel component you observe is affected by the velocity. So instead of in a real space, you would have a circle which is somehow quenched if you are observing in redshift space. So the task is now to include these velocities into your model of the correlation function. And there's a nice model, which is called the Gaussian streaming model. It basically tells you, consider density and velocity in a joint probability distribution. And now it helps you to relate the real space correlation function here, so real space R, to the redshift space correlation function. And the reason why we have an X here is just indicating that we are not looking on dark matter, but on biased traces. So for example, halos or galaxies. So there's a biasing, of course, included there. And the Gaussian streaming model basically tells you that you can take your real space correlation function and convolute it with a Gaussian velocity distribution. And the parameters that will enter here depend on scale. So you actually have to do predictions for the pairwise velocity and the pairwise velocity dispersion. And those Gaussian parameters can now be determined from Lagrangian perturbation theory. So on the one hand, we have the Gaussian streaming model, which tells you redshift space correlation function is connected to the real space correlation function and some velocity statistics. And all those ingredients you can now determine in Lagrangian perturbation theory. And we did this, so there has been a study before concerning the parameters. And we now compare always what is the usual prediction from the dust model and what is the prediction from a coarse-grained dust model. And what we observe, if you want to make a good fit for the correlation function in real space. So the first thing that is nice, we plot here several mass spins for the halos. And if you normalize them with respect to their bias factors, they basically all overlap and show this quite coherent picture of the real space correlation function. For the real space correlation function, the best smoothing scale you have to employ is 1 megaparsec over h. And this is the same smoothing scale we saw for the vorticity. And another interesting point is you can also determine what is the pairwise velocity. One time for the usual dust model, which are here, the solid lines. So the usual dust model is here. And if you again coarse grain it on a 1 megaparsec scale, you improve the prediction on the small scales a little bit. Still, you see that the description for the pairwise velocity is not that good on small scales, which is simply related to the fact that the Zeldovich approximation will fail, since there will be also accelerations. But now you can say, okay, I know this is basically the mean of my Gaussian. And on the other hand, I have the width, which is described by the pairwise velocity dispersion. And the effect on the pairwise velocity dispersion by the coarse graining is quite huge. So we compare here standard dust model, different mass spins. The prediction for the pairwise velocity dispersion is totally off of the data. So the data points basically show that for all masses, you observe a similar value of the pairwise velocity dispersion. And if you smooth that on the Lagrangian scale I already talked about, which is quite good for displacing the halos, you actually get really improvement on both the amplitude and also the shape. So what is now nice, since we know we have this Gaussian streaming model, which works quite well, the only task we have is to determine the parameters accurately. And we observed that we have a twofold scheme for the correlation function in real space and the velocity, the pairwise velocity. We have to employ this 1 megaparsec smoothing. But for the velocity dispersion, we get the best agreement if we use the Lagrangian scale. And now we can combine these predictions to actually compute the correlation function in redshift space. And the correlation function in redshift space is usually shown in terms of Legendre moments. So I basically split them in Legendre polynomials. And what you see there, so basically the first moment, which is the monopole, is here plotted in magenta. And in comparison, we have the real space correlation function in blue. So you see the monopole basically reproduces what the real space correlation function look like. There are some effects, but they are not big. So for the monopole, you are perfectly fine if you are doing usual perturbation theory with the dust model. But for the higher poles, so the quadrupole and the hexadecapole, it is quite important if you smooth or not. So I show here two examples for different mass spins. Each panel is the quadrupole and the hexadecapole here. And we compare the usual Lagrangian perturbation theory for the dust model in blue. The data points you see also in blue with arrow bars. And we show smoothing only on 1 megaparsec scale, so all predictions smoothed on 1 megaparsec scale. And our so-called hybrid model, where you smooth partially on 1 megaparsec for the real space correlation and the velocity, and on the Lagrangian scale for the velocity dispersion. And you can see that you're really improving your data. And it's kind of difficult to make the improvement overall, because you have several monopoles, and what sometimes happens, you tune your parameters and you think, actually, I'm really improving my prediction. But if you look at the next higher pole, you will see that you're actually not improving at all. So it's really difficult to improve this model, but we see if we assume that we have this hybrid smoothing scales, you can just plot it and you see it works well for all poles. So if you combine the coarse-grained dust model with convolution Lagrange perturbation theory, you get a real good prediction for the redshift space correlation function if you have these two smoothing scales. So for the quadrupole, it's not that relevant, but you see, for example, here for the hexadecapole, it looks totally different. So
Which of these curves corresponds to the original Jordan? I mean, like the Carlson et al.
yeah, exactly. That is the Carlson et al. And it was computed by Wang, the blue dashed.
Something's going wrong. No, I mean, like, this is Martin White's CLT you're talking about here?
Martin White basically also used the smoothing of 1 megaparsec.
Maybe you might be misinterpreting what they're doing. But okay, well, we can maybe talk.
So basically, what we did, we just applied, there is a code from Wang et al. So it's a paper from Wang, White, and collaborators. And they provide a code which actually compute all these parameters. And we adapted this code just for the coarse-grained dust model. And these curves are basically reproducing what their results are. Maybe they are shown in a different way in their paper.
It's just that in Martin's version of this plot, you know, for the quadrupole, it matches.
Oh, okay. You're referring to the Zeldovich streaming model paper, like recently?
No, this is older. Okay, anyway, well.
Okay, we will talk later about this. So actually, the message is, so the nice part is, this whole coarse-grained dust model has really complicated effects on the perturbation theory. But in the end, you can easily implement this by just taking the input power spectrum and smoothing it. So we compared the prediction basically for the whole theory calculation and the naive implementation of just coarse-graining the input power spectrum. And the good message is you can just coarse-grain the input power spectrum and it will give you both. Basically what you theoretically would expect. And on the other hand, it really improves the prediction for the correlation function in redshift space. So let's conclude. What did we see so far? First, I presented a Schrodinger method which models cold dark matter using a self-gravitating scalar field which solves the Schrodinger-Poisson equation. And I showed that it's a nice analytical tool because you get all the cumulants for free and in an analytical way. And it is indeed describing multiple streaming and even halo formation, so bound structures. Then let's show the nice video again. Then I presented the coarse-grained dust model, which basically can be treated in full analogy to the usual dust model, but has an interesting property concerning the vorticity. What is work in progress is the halo correlation in redshift space, and I just showed you a few plots. Basically, the message is you can improve your prediction if you smooth, but you have to think on which scales to smooth. And what we observed, if you perform a hybrid smoothing, you can really improve the prediction for the halo correlation in redshift space. So now you can ask, okay, what can we do in the future with this? So first, an interesting point about the Schrodinger method would be to actually investigate the role of this H-bar, because we saw H-bars important in the time evolution. And we could now ask, for example, how would a perturbation theory for the Schrodinger method look like? And this would, in the end, hopefully allow to disentangle the limitation of our model. One limitation is due to the fact that we're just considering the dust model, which is not actually solving the right dynamics. But on the other hand, it is limited because we are not able to solving dust identically and just stick to perturbation theory. And so far, we don't really know, is the main limitation due to the dust model or more to the perturbative expansion? So it would be really nice to have a comparison of this. On the other hand, since we saw that the Schrodinger method is able to describe bound structures, it would be quite interesting to ask, what would be the predictions, for example, halo density profiles or pseudo density profiles that are observed in n-body simulations and seem to be really universal. Another nice thing about the Schrodinger method, you can adapt this to several dark matter models. So one model basically claims that the Schrodinger method is not an approximation, but indeed describes what is going on. Then you would say, okay, I don't have really cold dark matter, but more a wave-like cold dark matter form, for example, the axion. On the other hand, you could even implement warm initial conditions and also describe relativistic neutrinos, which become later non-relativistic. So for one thing, you can just say, okay, let's stick to the Klein-Gordon equation then. So that's basically possible and can be just included in the Schrodinger method. So yeah, thanks a lot.
So for a given point in the quantum space, how long does it take to compute one set of spectra? Can you do MCMC with this?
So basically, so far, we just took the code from Wang et al. And computed it with that. We are now in the process of improving the code and really to make it shorter in time. So yeah, it will take. Yeah. Well, right now it is comparable to the original Wang code because basically what you do, you take the prediction and just move the input power spectrum. But I really expect that you can speed the code still up because there are really some points which are not optimal right now.
Okay, so I think we can